when we are speaking about glaciations and we're speaking about ice ages, we most often refer to the last period of glaciations, and that will be around 2.6 million years ago when it began. So 2.6 million years. How much is that? 2, 6, 0, 0, 0, 0 years. So you can just translate it into your Chinese scale. So that's when approximately 2.6 or 2.4, depending on the actual theory. So that's when it all began, and it lasted until 12,000 years ago. So that's how you can remember. This is the last ice ages, the Pleistocene era that we're talking about. And within this period, we have to identify the LGM and the LIA. The LGM is the last glacial maximum, so that will be somewhere around there, 20,000 years ago. So it's pretty much around the end of our last ice ages. And the little ice age will be actually after what we would consider the ice ages, and it's like 500 years ago. So this is little. And only 500 years ago, when we found a period with lower temperature around our planet. So that's why I just wanted to highlight here, when did the Pleistocene, the period of the last ice ages, happen? 2.6 million years ago it began. We had, we considered the end around 12,000 years ago. We had the last glacial maximum when there was a global cooling period around 20,000 years ago, and a little ice age 500 years ago approximately. But this is already not considered to be a part of the Pleistocene. Also important when we're speaking about the glacial environment is the integrated deformation profile. This is also something appearing in the exam pretty often. So integrated deformation and profile. So how does a glacial ice mass transform and move? And here there are three components of this one. The ice itself will be transforming, so internally deforming. there will be sliding and there will be a deformation of the bed. So how we draw this, how we speak of this, where we need to think of a surface on which top of there is the ice. So this is then the ice here, the ice mass. And how this is moving, well, on the surface we can measure the movement, really, because the whole mass, it will be transforming as well. And so there are three components again. One is that the ice mass itself will be internally deforming. And as we know how ice is behaving, so that's how we measure on the top, there will be a larger velocity on the surface. So this is the internal deformation. There will also be sliding on the surface of the bed. And depending on what kind of material we have here, and whether it's a cold or a warm based glacier, this will be a different value. We might say when it's a hard, solid rock surface, then there's a higher chance that the ice will be sliding faster. So this is basal slide over there. And there is one more component of this total movement, which is about the dilation. So whenever we have a soft bed made of usually unconsolidated materials, sand, rocks, gravel, and bed transformation, so that's the bed itself will be that is moving, and this contributes as well, not only with the sliding and the internal deformation, but with this dilation there will be a bed transformation. We can also call it a bed deformation. Here I'm just using this term to describe that this material will be moving faster on the top, and the ice is carrying also this material. So that's how we can just imagine the three components that contribute to the movement of the ice surface, if we're talking about glaciers or ice streams. And then this is then the integrated deformation profile. As we are speaking about the deformation of the ice mass, we can right away talk about how ice is behaving. We said it's a non-Newtonian fluid. And what does that mean? That it's non-Newtonian. And fluid, where that means that its viscosity can change depending on the stress level. If we think about coordinate system, so this chart, where in this case I'm just going to put to the horizontal axis down the bottom the stress rate, and I'm going to put this strain on the vertical axis, which also means strain velocity we can call it strain velocity or strain rate. These are different terms we can use, and stress rate over here. This would mean the force, and that would mean how deformation of the material can happen. Now we know that there will be a straight line here for water, and that would mean that the stress rate and the strain rate are moving in the same pace. Basically, the viscosity would be this line. Viscosity would mean then that it will be able to flow in a same rate independently from how much stress we apply. If we squeeze the water, if we pour the water, or the water is still without any pressure, independently from that, it will be acting as a liquid in the same way. Now, if we think about other materials like blood or paint, we can say that in some cases, and I'm just gonna draw this like such a curve here, but it can be of course different depending on what material we're speaking of. So blood or paint, or also ice, we will see that if we don't put much pressure on the material, so there's a low pressure, low stress, then it will have a lower strain velocity. Actually, it will act like a solid. But as we increase the stress rate, then the strain rate will start increasing. It will also mean that it can act much more like a fluid, so the viscosity will change. And what we also want to know about is the other example, where as we increase the stress, the strain will drop, so it will more act like a solid material. And that was the case when we speak about oblique. With cornstarch and water being mixed. So these are both non-Newtonian fluids. Oblique and ice, in our example, are both different from water, but in another way. And what we have here and call pseudo-plastics So these pseudoplastic materials are the one where with higher stress, the more movement we experience, whereas with cornstarch and oblique, with the example that I show you, we experience an opposite form of transformation of the viscosity. So both are non-Newtonian fluid, but we just want to know that the example that you so often see in scientific like experiments or on the internet, oblak, is different from how ice is a non-Newtonian fluid.